Right. Well, thanks. Boy, I think half of Australia is on this Zoom call. It's my impression anyway. So very nice to see all of you. I'm sitting in my cold basement, but of course it's summer out here, so it's about 28 outside, and so I'm suffering on your behalf. Okay, so this paper is one that is going to come out any day now. I'm sorry that it wasn't out, so you could have had a look at it before, but it's myself and Bernie Bauer, and it's primarily a review paper, but within it there is an extension of the original RDA conceptual model into something that I think is a lot more robust than that 2005 one was. As soon as it's out, I'll let Kristen know, and it can be passed on to everybody. So the context here for the talk is that obviously eustatic sea levels rising at about 3 millimeters a year, and it may increase. There's all kinds of concerns for impacts on salt marshes, mangroves, coral reefs, sandy beach systems, and of course, potential impacts on the human. And there's lots of dire warnings, mostly in nature, climate change, I think. One of those is a paper that was published by Vosdukas et al. In Nature Climate Change in 2020. It's sandy coastlines under threat of erosion. And there was a discussion in response to this, a discussion by Cooper and a very large group of people. So one of the things that this paper suggested is that the sea level rise and ambient trends in shoreline dynamics could result in the near extinction of almost half of the world's sandy beaches by the end of this century. That's a pretty catchy kind of thing to have to look at. It's a paper that's based on a very thorough study in the EU and it's carried out by reputable scientists and coastal engineers. And so the question is, are they right or are they wrong? In my view of it, the key question is, would we really expect this loss of sandy beaches, given our understanding of the way beaches, or nearshore beaches and dune systems operate? And at the end of it, I'll say, obviously, that I don't expect that. So a key factor here is, of course, the Bruun model, which has been used now for, I don't know, it seems like a century, but it's probably about 60 years. And a key aspect of the paper that Bruun produced in 62 was that he assumed that with sea level rise, you have erosion of the berm and beach area, and that volume of sediment is transferred to the outer near shore, that is the area seaward of the breaker zone, and that it builds up to a level that's equal to the rise in sea level. So it's quite a neat thing. Everything balances nicely. The volume here balances that, and the increase in the height of the sea level of the bed is equal to that of the increase in sea level. As part of this, he also had this equation which allowed you to predict the distance that the beach system would transgress as a result of that increase in relative sea level. And that was then called by Maurice Schwartz the Bruun rule. So Vosdukas et al. Basically assumed that Bruun was valid, and in the modeling they did, therefore, it's not surprising that they concluded that the beaches were going to erode. You can't use Bruun without having the erosion unless you have an awful lot of sediment coming in, say, alongshore or offshore, from the offshore. So in 2005, I put forward a very simple conceptual model that was really intended to mirror the Bruun rule, because it used an equilibrium profile. And in that, it essentially said that instead of sediment being eroded from the beach and dune system and being transported offshore, that in fact the whole profile would migrate landward and upward. So that would be the nearshore, the beach, and the foredune would migrate upward synchronously with rising sea level. And the obvious benefit of that is that Since the sand is coming onshore, the sandy beach systems get preserved. So the objective of the paper that we've just done was to verify the assumptions of the update, or sorry, my objectives here to verify the assumptions of the update that we did to the conceptual model. And so I'm going to describe that conceptual model as it now stands, and to go into a little bit of detail about what my expectation is to how beach and dune systems will adjust as a consequence of relative sea level rise. And at the very end, I want to say that part of the push to do this came because I really wanted to see if people would make use of this alternate view of what happens with sea level rise on sandy beaches in predictive models that could be used, for example, for coastal management. So in the new system, in the new model, instead of having an equilibrium profile, what we've done is to divide the shore profile into 3 areas of interest: the upper shore face or near shore, the beach, and the foredune. And there's some indication here of the kind of time span for sediment transport processes working within this. While we assume that there is a dynamic equilibrium in each of these 3 areas, we allow for some small amount of sediment to come in, say from the lower shore face into the system, and also some sediment to leave the system landward of the foredune, so that might be into a dune field, it might be into a back barrier marsh. Okay. There are a number of assumptions in this, but the one that's really critical, I think, is that, first of all, that the relative sea level rise is less than 10 millimeters a year. And I'm working usually with 3 to 5 millimeters at the moment. And also that the hydrodynamic and morphodynamic changes that we see in the nearshore, the beach, and the foredune are a couple of orders of magnitude greater. And this is something that isn't always the case, and there is an example from the Great Lakes in the last few years that I will share with you maybe after the talk is over. And I'm operating on a time scale of decadal to a century. And that's primarily because when you get much longer than that, you really have to take into account the evolution of the coast, so things will change. All right, let's begin with the nearshore beach interaction. And I'll just go back to the sort of seminal work of Shepard in 1950, who put together this profile oscillation with the 2 end member states. In the winter, we have storm waves, they erode the berm, bars are formed offshore, and the beach profile is very flat. In the summer or fair weather conditions, we have a profile that returns with the bars migrating and welding to the beach and a big berm being formed. And so what we now know, of course, is that there are a whole range of possible combinations and end members, depending on whether you're in Australia or California or the Gulf of St. Lawrence, where I do a lot of my work, the east and west coast of England, etc. But we can assume that in any one of these locations, there is a dynamic equilibrium in the profile form, that basically you've got an envelope of profile changes, and you could probably put some sort of average profile through that. Of course, the Shepard model was very much improved upon by, or at least enlarged by, Wright and Short in Australia, and I'm sure some of you are probably familiar with this. And so we now see from work that's been done all over the world now that there is a wide range of possible forms, and that in many cases the changes that we see in the nearshore operate over a much smaller proportion of the potential range. This is from Castel and work on the southwest coast of France. And in the previous zoom in that I did, I took a little bit of work from Daudet et al. On the 2013-14 season, winter in Western Europe, which was particularly severe. And this is actually some data on the beach volumes in the period before 2013-14. Then the red here shows erosion that's associated with a number of really severe storms. And then the green shows the recovery of the beach system over about 3-year period. So this is what we expect to see with nearshore beach interaction, is periods of storms result in erosion of the beach and transport offshore, and the intervening fair weather, not necessarily fair weather, but smaller storm periods result in the rebuilding of the beach. And of course, if you have really big storms, and this is the gray line here, they also erode the star slope of the dune, and we find that the dune that takes a little bit longer to recover. So in summary, and this is all, there's a lot of literature on this in the paper itself, but what we can see is that the changes in the beach and nearshore morphology happen continuously. They're happening on a periods of hours to days to years, and that the morphology oscillates within some envelope that we can define. And those profile adjustments are usually in the order of centimeters to meters, as opposed to the relative sea level rise, which is in the order of a few millimeters, as you can see me saying there. So I think what I would expect to see then in terms of response of the nearshore beach system to sea level rise is that those processes should be maintained in dynamic equilibrium, and that the whole zone will migrate with the rising sea level. Okay, let's go on then to look at the beach dune interaction part of it. And I have to say that one of the things that always bothered me a bit about Bruun was that he didn't have dunes in his models. And I think we should love our dunes. So this is part of what is important. So with the beach dune interaction, we've got the area out here, which is primarily wave driven. We've got the beach itself, in which we have transport by both water and by wind. And then we have the dune itself, which is fed by wind, transporting sediment from the beach into the dune itself. We have a similar sort of system happening here in terms of response to dunes and non-dune conditions. So in a large storm, then if the setup and storm surge is enough, then we will get waves that will reach the base of the dune. They will erode the base of the star slope and scarp it. Large scarps and small scarps for small storms and large scarps for larger storms. Slumping from the scarp builds up, initiates the buildup of that dune ramp, and then over the next days, weeks, months, the dune ramp itself builds up as a result of aeolian transport. We always think of it as coming onshore, but in fact, much of the dune ramp builds up from oblique and even longshore winds. And as it gets closer to the top, there's a much more complete profile for sediment to go directly from the beach and up the star slope. So this can take months to a few years for modest things. Really big storms, it might take you a decade or more to rebuild the dune. Here's a look at a couple of shots. The one here is from Greenwich Dunes in Prince Edward Island, which is in the Gulf of St. Lawrence, where we've done a lot of work. And this is another one from Skarland on the Jutland coast of Denmark, where we did a bit of work with Trollsøygard. These are after two large storm events. This one here happened in December of 2010. This one just a few days before this picture was taken. So after the storm event, you've got this beach slope, which is your storm beach slope. And the point here marks where the wave erosion of the foredune ceased, if you like, where the recession of the foredune due to wave action ceased. So that point is, if you like, it's a point on the trajectory that is taking place as sea level rises. So if we look at this situation maybe 10 years down the road, another storm of similar magnitude would produce the same waves, the same setup, but now water level after 10 years is, shall we say, 50 centimeters higher than it was previously, so that we would expect this trajectory point to be 50 centimeters higher along that, along a profile slope defined by this. So maybe 3-4 meters further into the dune than it is there. So if we map out each point for these major storm events, that should map the rise of the dunes itself and of the beach system and the distance inland that it goes. Okay, so up until now, we've been assuming that everything is in dynamic equilibrium. Most beaches aren't obviously in a state where there's exact matching of inputs and outputs. And so I wanted to take a look at what's happening on this section, which is the Greenwich Dunes, where we worked for about 15 years, I guess. And I've done so in part because there is a very distinct transport of sediment from left to right. And in this portion up here, the littoral sediment budget is negative. And as you move in this direction, it becomes more and more closer to positive. So by the time you get down to this profile here, line 8, it's probably neutral to slightly positive. And we'll have a look at some information from these 4 profiles here, which mark the transition from negative towards neutral or positive. So here's a picture taken from the crest of the foredune, looking back towards line 5 from line 6. This is after the storm, December 2010 storm, and you can see then the beach, the truncated star slope, the top of the erosional scarp here. And this is the same, roughly the same location back in 2016, so 5 years later. You can see the sediment that is built up here of the dune ramp, now colonized by vegetation. And you can see on the beach itself, this is all the berm, the backshore area that has also been colonized by marram grass in this case to form an embryo dune, or as Patrick would have me say, an incipient dune. So this is the recovery phase then. And you can see just a little bit of of a scarp slope here. This is not actually the original scarp, because in the period there was some, so the scarp itself originally was out here, and there was a winnowing of sand from the crest itself. I want to show you these. Bernie doesn't like this particular thing very much, but these are measurements of sediment accumulation from the star slope to the lee slope. We've lost the star slope stuff here, but it's measurements on an annual basis, and you can see how in each location we can see differences in the amount of sediment deposited each year, and differences in as we go from the crest towards the base of the lee slope. In this one, we've maintained the upper stars on the crest, and when we get to line 8, we've got everything here from the beginning. The mid stars, upper stars, crest, mid-lee, and the base. So what it shows is that on the dune itself, sediment is being transported up the star slope, over the crest. It's been deposited on the crest, the upper slope, and it's been deposited all the way down the lee slope. And that's happening on an annual basis. And in fact, it's happening in many events during that annual basis. So here are profiles from 3 of those lines. Line 5, where the littoral sediment budget is negative. And the red is the profile in 2002. This dark color black here is the profile in 2016. So 14 years of profile data. We have mostly annual data, but I've left the India ones out. So here where the profile is, where the sediment budget, littoral sediment budget is negative, we can see a transgression of the dune system. In this case, over about 10 meters, 10 or 12 meters. We can also see that during this time, if I can get my thing back, the dune crest has grown upward in elevation, so that final elevation is much higher than the original elevation, and we have deposited sediment on the lee slope to quite a thickness. So the budget here is negative, but the dune sediment budget is essentially being maintained. It's maintaining its original volume, and it's actually moving landward and upward at the same time. If we go to line 6, we find that this is closer to the neutral part of the littoral sediment budget. So there's only a small retreat over that same time period and a very small retreat in the dune crest, but we still get sediment building up on the lee slope. And finally, at line 8, where we have a neutral or slightly positive littoral sediment budget, the toe of the star slope oscillates back and forth, reflecting storm events and non-storm events. But over this period, what we have is an increase of 2 meters in the height of the dune. So it's now gone up to 11 meters. And small amounts of sediment are still reaching the lee slope and building up. So here, the littoral budget may be roughly neutral. The dune sediment budget is still positive, and that reminds us that the dune is a sink for sediment from the beach, and so some of that sink is restored when we have large events scarping the star slope, but some of it may be going on here and into the area landward. Okay, so again, the summary is that these changes in the beach and foredune morphology occur continuously. They occur over weeks, months, years. It's a bit slower than for the beach, but it's still pretty rapid. Especially, we're looking at profile adjustments that are much greater than any changes in the sea level. So again, we assume that the beach and foredune profile should be maintained in dynamic equilibrium, and that the foredune recovery balances the episodic dune scarping. As a result, then the foredune will shift landward synchronously with relative sea level rise. Okay, one of the things that came out of this was an alternative to the Bruun rule, and that's Robin's rule. The equation looks the same as most things. It's basically a transgression distance, a time period, a change in the sea level, and a slope angle. But in this case, the key thing is that I'm defining the slope angle as the slope of the beach after a major storm event, as I showed you on the pictures of the things. And a key thing here is that this, for the decadal or century scale that I'm dealing with here, means that we don't have to worry very much about what's happening in the nearshore, in the upper shore face, or even in the lower shore face. That the transgression can be predicted from the slope of the storm beach alone. If we look at sort of a typical range of storm beach profile, 1 to 15 to 1 to 40, and assume a sea level rise rate of 3 millimeters a year for 100 years, then that gives us a range of transgression on the order of 4.5 to 12 meters. And if we take those same slopes and up the sea level rise to 5 millimeters a year, then the range of transgression is 7.5 to 20 meters. So it's not a huge amount, but that's just the sea level. We're not accounting here for any kind of sediment budget effects. Okay, so there's lots of evidence for the onshore movement of sediment. A lot of it comes from papers that come out of, I read every day from the southeast coast of Australia, it seems. I'm going to, and we've referenced a lot of that in the paper. I want to look at the situation in the Gulf of St. Lawrence because it's an interesting one compared to the sort of Holocene sea level rise. We're working here in Greenwich. This is Prince Edward Island, and this is New Brunswick in the Gulf of St. Lawrence. The red lines all map out a whole series of barrier systems, including these here in the Ile de la Madeleine. A key thing here is that in PEI, because of hydroisostasy, I'm sorry, I'm getting late for me here. Because of hydroisostasy and also the collapse of the forebulge, this area is essentially suffering isostatic depression. And so for the last 6,000 years, the sea level rise here has been roughly 0.3 meters per century, or 3 millimeters per year, which is what we're experiencing now. We have modern tide gauge records that show this, and then Don Forbes and his group have gone back 6,000 years to map this out. We can see this in a whole series of barrier islands in the Gulf of St. Lawrence. This is on the New Brunswick coast with barriers, overwash, tidal inlets, estuaries, and lagoons. Sorry, I didn't mean that. And here's another example from Prince Edward Island. And again, very similar barriers that quite narrow in places, lots of overwash, lots of tidal inlets and tidal deltas. So where's all the sand going? To me, this is a key factor here. And here, this is side scan sonar mapping of a large part of that area by, again, by Don Forbes and his group. The red and the oranges and yellows represent bedrock. The blues represent sand, and they don't extend right to the shoreline because the boat they were using couldn't get any closer than this. But basically, almost all of the sand is in this area here. And this area is effectively a ravinement surface in the sandstone bedrock. It's a really nice spot too, because that's where all our lobsters are. And if you're out diving, you can always get dinner. So where's the sand going? Well, it's going into it's out there in the nearshore on this on nearshore bars. It's in barriers, and we see overwash landward across the barriers. It's in the inlets between barriers, so it's in the ebb and flood tidal deltas, and some of it's transported up here. Where we have large dunes, it's some of this is migrating landward rapidly, where we have blowouts, and where we don't have blowouts, we just get lots of sand coming over up the star slope, over the lee, over the crest, and down the lee slope. So these are the ways in which migration of the sand is taking place, and the whole coast here seems to be migrating quite happily for 6,000 years, preserving all the barrier systems. Am I okay for 5 minutes more? Yeah, okay. So obviously it's nice to use, we can go from equilibrium profiles to dynamic equilibrium, but there are obviously complexities that occur. Some of this is what's happening out here on the lower shore face. And as I say, there's lots of work done, Kinsella and Peter Cowell and so on what's happening out here. In general, what we've assumed is that this amount coming in is a relatively small amount, but it could be larger. What we assume, though, is that the amount of sediment that's coming in from the shore face, if there's any coming in at all, is probably relatively constant over a time period of decades. It may well vary along shore, as we know. The other thing that we have to look at is what's happening at this end of the skiing. Over a few decades, if it's just sea level rise that's taking place, then this migration will be a relatively moderate one. But if you have a system where you've got sea level rise superimposed on negative littoral sediment budgets, then this may be migrating at 50 or 100 meters a year or more. And so that what's happening landward of the base of the foredune is also important. So for the complexities on the seaward side, we can look at what happens in the lower shore face as we raise the sea level. The wave base will rise, and the sediment that's there will tend to move landward, feeding into the upper shore face. And the amount of sediment will be limited at some surface level, and that's our ravinem surface, which here I've shown in perhaps Pleistocene sands. Where you have bedrock close to the surface, then this limits the amount of sediment that can move landward, and so the supply to the upper shore face will be a lot less. As we go from there to there, there's relatively little sediment available, and so the feeding to the near shore is quite small. So, I'm sorry, I should say that this develops a ravinem surface in bedrock, as we saw for Prince Edward Island. And let's look at the complexities on the other side, because as I said, if we look at migration over centuries, or if we look at a situation where we have sea level rise combined with a negative littoral sediment budget, then the situations can get a bit dire. So here we have, as we have in many parts of the world, some sort of urban infrastructure, some sort of human infrastructure landward, and then this will stop migration at that point. The simplest situation exists on a natural beach, a natural system, where the slope is roughly the same as the transgression slope. And so if Robin's model is correct, then this whole thing will migrate, maintaining the dune system and the nearshore system and the beach. And the beach should remain the same width. These should remain largely the same. It gets a little hairier when you have a positive volume. That is, your dunes are now migrating into something like a dune field landward, and so you end up with a lot of things. And obviously, this will slow down the rate of transgression. So you might predict from sea level rise 15 meters over a century, but it would be less than that if you've got this large dune field in front of it. And obviously the one that attracts most attention is when you've got this negative volume. That is, you've got a barrier system here with a flat slope or even a slope down to a lagoon. If that dune is transgressing, then it has to fill this space here in order to maintain its height. And if it can't fill that space, if there isn't extra sediment coming in from offshore, then the situation that we mapped out here is what will happen is that as the dune migrates inland, it's losing some of this volume to fill that, and eventually it'll die out. So these are just very simple examples of it, and I'm sure all of you are aware of many more and know much better about this than I do. Okay, so I want to end here with the last bit, which is part of what sort of drove us to produce this thing, and that is, how can we take what we understand about the nearshore beach and foredune system and apply that in models that would be used to predict what happens to the sandy beach shoreline over a period of decades to a century. So we've got models around Delft 3D and X Beach, for example, doing stuff in the subaqueous realm. Recent models, Hoonhout and De Vries, and then a more recent one by Van Rijn and Stripstein in 2020. So there are models now that allow us to predict sediment transport from the beach into the dune. And another recent one is by Cohn and a large group, including Peter Ruggiero and so on, where they've coupled these three so that you can model stuff from the subaqueous to the beach the dune. But clearly, if you're going to do that for decades to a century, you're going to need to do some kind of reduced complexity modeling. And two that I've looked at are ones by Hallen et al. In 2019, and this is an update of one that they just did the aeolian component, and McCarroll et al. In 2021. And these are, to my view, really excellent examples of where we should be going with this. Not me, because I'm not going to be going that way with it, but where things should be going. My only complaint about these two particular models is that they use the Bruun model, and they all calculate a sediment transfer from the beach and foredune to the nearshore profile. And as a result, and this is just taken from Hallen et al., the dunes disappear really quickly. And so what would happen if you just tweak these models a bit and had the whole thing translate, as Robin says? That would be interesting to see anyway. So that's, look, I'm being a bit, you know, I'm being a bit, how shall I put it? Let's see. I can expect that, or we can expect that many sandy beaches will translate synchronously with sea level rise. That's really the take-home message. That's what Robin's model says. And I don't think that we have any evidence, I've certainly not found it, of sediment accumulation seaward of the breaker zone building up as sea level rises. And I think this occurs basically because of all the work that people have done on the nearshore, you know, going back to Andy Short and Don Wright, and even a little contribution from Robin in the days that he actually put his wetsuit on and went underwater, and on the beach, and now in the foredunes. And I think we now know enough about the way that the foredune works to be able to include that in models of response to sea level rise. So thank you. Yeah, skip that.
Thank you very much, Robin. That was
okay. Let me.
Interesting. And it's in a virtual clap. I haven't yet figured out how to do all those. Does any